Today I shall try to move towards quantum mechanics, and I think I will be able to cover more than just lecture 4 today. Lecture 4 is actually very short, right? But we'll see what happens. Just to recapitulate what we did last time, the idea is really to distill all of classical mechanics into just one quantity, the action, right? Although I had shown this only for one free particle, and actually the notation I used was only for one dimension, you can easily see that it generalizes to much more complicated situations, many particles in 3 dimensions. I leave it as an exercise, which I did not assign to you, to go beyond motion of single particles. See whether you can cast all of Maxwell's equations into an action. Use a least action to obtain all 4 Maxwell's equations, all right? That goes beyond particles to fields. But the whole point is essentially all of classical mechanics, so long as there is no dissipation, so long as you confine yourself basically to conservative systems, can always be distilled to one quantity, the action. And the idea, if I go back to the example of one single particle in one dimension, so the red line represents the correct path. The correct path has minimum action. And the neighboring paths, differing by some small quantity in eta, would have an action that is the minimum plus something of order eta squared, because the first order variation vanishes. All right? So that's the essence of classical mechanics. And in classical mechanics, only the red line matters. Only the correct path matters. The other paths, you use them in the intermediate calculation. But actually, they have no physical meaning in classical mechanics. A particle does not actually, any time, go along the green path. Right? Now, in quantum mechanics, we shall see that, in fact, in some sense, the particle goes along all paths, including all the green paths. And in some sense, not just the neighboring paths. In fact, it could go everywhere else. And by considering all possible paths, we shall arrive at quantum mechanics. That is the essence of the story. Right? So let's start with some simple ideas. And today in lecture 4, lecture 4 is going to be very simple. Deal with the phase factor for one path, then consider some thought experiments with multiple slits, interference, and so on. And that will take us to the idea of summing over many paths. And I will then go back to the classical limit from this point of view. And in some sense, you can, quote, derive the least action principle by these very simple ideas that arrive from the idea of waves. Right? So let me start with phase factor for one path. And I will start with plane waves, so things that you know very well. So psi, the first line, is a plane wave. A plane wave goes like e to the I times the phase. And the phase factor for a plane wave in one dimension is the wave number k times x minus the frequency, angular frequency omega times t. That's something you know very well. Now, when I write this down, I am already assuming something which is conceptually very important and which Professor Yang, I'm sure, has talked about, and that is the transition from a real wave function to a complex wave function. When you first learn about waves, it would not be e to the I something, but say cosine of something or sine of something, right? That is a real wave function. And you write it as an exponential. You can write it simply as a mathematical convenience, meaning you always take the real part. Okay? That makes life simpler when you say differentiate. But in the back of your mind, in classical physics like EM waves, sound waves, vibrational waves, whenever you write something complex, you really mean the real part. But in quantum mechanics, that is not the case. Both the real part and the imaginary part have to be kept. You cannot simply take the real part. And I think the realization that you have to take the imaginary part as well, the whole thing goes together, and you don't just take the real part, is a very important conceptual advance in the early parts of the 20th century by people like Schrödinger and Heisenberg, right? So Professor Yang has talked about that story. That is the whole idea of the complex phase, all right? So I take that as given, right? You understand this. So this is a plain complex wave. You would write like this, all right? So that's the first concept. a complex wave function for a plane wave. Then the second idea that we have to inject, of course, we can't get everything by just thinking. There has to be some experiments. And the experimental basis of quantum mechanics, you know, even from high school, is Einstein's photoelectric effect, then leading to the equation on that side, omega is E over h bar, right? The equivalence or the relationship between energy and frequency. And then de Broglie's result from, say, electron scattering that relates the momentum to the wave number k. So these two are very simple equations you've learned years ago. Is a relationship between properties of a classical particle, E and P, and properties of a plane wave, omega and k, right? So that is the essence of wave-particle duality. That's something you know very well. So if I just put this result into the phase factor phi, then I can write the phase factor as 1 over h bar times px minus et, right? That's easy. And of course, we also know that the energy is represented by the Hamiltonian. So I replace E by the Hamiltonian H. Is this okay? So that's very simple. So from a plane wave and using wave-particle duality, I arrive at this formula. Now, actually, as a particle goes along in its motion, the momentum and the energy need not be constant, right? So you know what you should do. Instead of writing down a formula for the phase along the whole path, you chop up the path into little pieces. And for each piece of the path, you can, of course, regard the momentum and the energy as constant. For that piece of the path, you write down the little bit of phase that is accumulated, the phase change along that path. For example, a wave goes from here to here, the phase changes by this much. Then in the next segment, it increases by a further amount, right? So the total phase is the sum of the phase changes along the path, and for each segment of the path, delta phi, the increase in the phase, is p delta x minus h delta t divided by h bar. Okay? So just the previous formula applied to short intervals. Oops, what happened? Okay. Now, I pull out a factor delta t from the bracket. So in the first term, the delta x becomes x dot. Okay? I write this delta x. Oops, what happened? Okay. I write this delta x as x dot delta t. Is that right? Now, but you recognize the bracket now as px dot minus h. And that is, of course, just a Lagrangian. Right? Now, today I'm using very simple formulas. But you probably had not realized before that there is this very simple connection between the phase of a plane wave, right, kx minus omega t, and the Lagrangian. Okay? So that is, in a sense, a deep connection, but a computationally trivial one. So the phase along a path, a segment of path, is Lagrangian delta t divided by h bar. So if you add this all up, of course, the total phase along the path now becomes this integral of Lagrangian dt divided by h bar. In other words, the action over h bar. Okay? So I have derived a very simple formula that if I go along any path, the phase that is accumulated along that path is action over h bar. Classical action over h bar. And that is a very neat and mathematically elegant way of expressing the relationship between classical mechanics, a particle description, and wave mechanics. Is to say that the phase accumulated is action over h bar. Any questions so far? Right? So that's easy. So that is the key link between classical and quantum physics. Right? And of course, h bar appears. Now, let me consider now some thought experiments with multiple slits. And you have probably encountered discussions of multiple slits when you first learned interference, even in high school, right? Ripple tanks, you know, that's a multiple slit. You learned it in optics. You learned it when you first learned quantum mechanics, the ideas that even particles can interfere. You discuss multiple slits. And I'm going to use exactly the same idea. So let me consider an interference experiment let's say, electrons, right? So you have a source of electrons. Electrons go through two slits and arrive at the screen or detector on the right-hand side, where the position in the vertical direction I call x. Okay? Now you know what is the wave function that is detected on the screen. Because there are two possible paths, the wave function that you detect is the sum of the two wave functions that would occur along the two possible paths, right? And that is the essence of interference. So along one path, if the phase is phi 1, along another path, if the phase is phi 2, then the wave function you detect is the sum of the two, and that is the origin of interference. If phi 1 and phi 2 are in phase, the wave amplitude would be doubled, and the intensity would be 4 times. If they are out of phase, they would cancel, and there would be an interference minimum, right? That's something you know very well. So I write this schematically as the sum of EI phi over all possible paths. Now, in this picture, I have only drawn 2 slits. If you have 10 slits, then the sum over paths would have 10 terms, okay, schematically. Now, but I now look at not just one sheet of slits, but say 2 sheets, okay? So I have one obstacle with a number of slits, and then further down another obstacle with a number of slits. Now, of course, again, I draw all possible paths. A possible path is chosen by choosing one slit here and then another slit here, right? The choice of the first slit can be represented by a variable x1. So if x1 is equal to this value, it goes through this hole, x1 equal to another value, x1 equal to the third value. And then x2 can take on this value, or that value. Okay? So x1 represents the position in this plane, and x2 represents the position in that plane. Okay? So a path now is defined by all possible choices of x1 and x2. If there are, say, 3 choices of x1, 7 choices of x2, this sum will contain 21 terms. Now, I'm now going to make a conceptual generalization in 2 senses. One is that the choice of each x will be made continuous. That is, I would remove the screen altogether. It's all holes, right? You imagine making so many holes in here, adding more and more holes, okay? So that there is nothing left in this obstacle. So all values of x1 are allowed in some sense, all right? And I also increase the number of these sheets to infinity, okay? So I chop space conceptually into little segments. Imagine each segment, each sheet is now punctuated with many, many holes. Then it's just empty space, right? So the wave function as it propagates through empty space would be given by such an expression where there is an infinite number of such sums, one for each sheet, okay? Or in other words, because as the particle moves along, it gets to each sheet in each moment in time. So you can also think of, for each moment in time, there is an x. And each x takes on all possible values, all right? So there are 2 infinities, all right? The number of sheets, each sheet corresponding to 1 time. So infinite number of times. For each time, there is a value of x, and the value of x also takes on all possible values. Then it's no longer multiple slit. It is simply the particle propagating from one point to another point. Okay? So that is the conceptual jump. And this is, of course, the inspiration of Feynman in about 1950 or thereabouts. And you can read about all this in the very nice book by Feynman and Hibbs, which is in your lecture notes. And just to give you a bit of history, the path integral formalism was written down by Feynman in the early 1950s or late 40s, just after the war, and was not much used, except that he used it as an inspiration to get his Feynman diagrams. But people focused on his Feynman diagrams and didn't worry about the path integrals. He taught a course on the path integrals at Caltech, and Hibbs was a student that took all the notes and ended up in this famous book. And nobody noticed it very much from then until about the 1970s. when people came to theories such as gauge theories and found that if you want to deal with the quantum version of gauge theories, the path integral is much more effective than the conventional treatment. Now, for reasons which I won't be able to go into. But now, whenever you deal with quantum field theory, the first thing you write down is always the path integral. Okay? Because just like when you do classical mechanics, the first thing you write down is F equals ma. Okay? So just to repeat what I have just said, now no longer think about a number of screens, but the horizontal axis, think about it as t. Okay? So I chop it up into intervals at times t1, t2, t3, and so on. And for t1, there is a variable x1. For t2, there is a variable x2. And a sum over paths means sum over all x1, all x2, all x3, and so on. Okay? And once each term in this sum represents a choice of x1, a choice of x2, a choice of x3, and so on. Once you have made those choices, that means you have fixed certain points in this picture, right? In this space-time diagram, I choose an x1, I choose an x2, I choose an x3, and I join up all these points, and that is what I mean by a path. Okay? So this is a discretized version of a path. In other words, a path, I said, was represented by a function x of t. Now I represent it by a set of numbers, x1, x2, x3. Okay? And the path you mentally think of as just linking these points by straight lines. Okay? So this is a discrete version. And of course, mentally, we in the end always take the limit of everything, all the little bits going to 0. Delta t goes to 0, and all the x's become continuous. So in other words, the schematic notation of sum over paths should now be written as sum over x1, sum over x2, sum over x3, and so on. Or in the continuous version, dx1, dx2, dx3, and so on. Now, I need to multiply by a normalization factor. The normalization factor, now, how many dx's I take, that is, if I have a finite time interval, I can chop it up into n pieces, capital N pieces. Oh, not capital N. Chop it up into, I don't know, m pieces. Eventually, I want m going to infinity. The normalization factor will depend on m. Okay? But in the following, you will see that I don't really need to tell you what the normalization factor is. It will simply be absorbed. Just write a normalization factor. So whenever I say sum over all paths, I mean normalization factor times this multiple integral, where how many integrals there are, there will be, say, m of them, and eventually m goes to infinity. Okay? And as a shorthand notation, this thing will be written as dx, capital Dx. And so the wave function is given by the path integral dx, sum over all paths. This simply means sum over all paths. What is the contribution of each path? It is simply e to the I phase. And the phase is action divided by h bar. Now, I say almost. I will qualify the almost later. Okay? That is the quantum mechanical wave function. Okay? So this is quantum mechanics. So in a very compact notation, the quantum mechanical wave function is obtained by sum over all paths e to the I s over h bar. Now, this integral is a very difficult integral in some sense, right? It's not a single integral, it's not a double integral, it's not a triple integral. It is an m-fold integral where m goes to infinity. And that is a new mathematical object which later mathematicians made rigorous. But heuristically, we will just sort of chop into m pieces and do it as m integrals and then take a limit, okay? Without worrying too much whether the limit exists in some rigorous sense. All right, so that is really quantum mechanics. That is the essence of the path integral in the book by Feynman and Hibbs. So I said almost. Now let me qualify what I mean by almost, all right, and write it slightly more precisely. And this involves the Green's function. Now, in in fact, in quantum mechanics, and in fact in any linear problem, I can't really say what the wave function would be at time t, unless I tell you what it is at time t equals 0, right? I have to give you the initial condition before you can calculate what the wave function is at a given time. So the formula I just wrote down cannot be completely right because that did not involve the initial condition. Okay? So now let me tell you how to incorporate the initial condition. So let me pose you a problem in quantum mechanics. I give you the initial wave function, psi of x and 0, and ask you to find the wave function at a later time t, psi at x prime and t. Well, what can you say? The thing you can say is the two must be linearly related. Okay? If the two are linearly related, that means the later wave function can be written as a linear superposition over the initial wave function. That's the most general linear representation. The coefficient I call capital G, and is known as a Green's function. It depends on three variables, x prime, x, and t. Okay? It's called the Green's function, sometimes called the propagator. It propagates the wave function from position x at time 0 to position x prime at time t. Right? And the idea of Green's function applies to all linear problems. It relates, say, the initial value to the value at time t, or the boundary value to the internal values, and so on. You can always define Green's functions. That's the most general description of a linear relationship. Just as if x and x prime are not continuous variables, but discrete variables, then they would be represented as a column vector. Right? If x takes on only three values, x1, x2, x3, then psi would be a column vector with three entries. And the relationship of one column vector to another, if it is linear, would be a matrix. And the matrix would have two indices, so G, X, X prime would be like X and X prime would be the row and column of a n by n matrix. Right? So this is just a generalization of a linear relationship to the continuous case, that's all. Now, although I won't use this in the later calculation, let me just tell you what the Green's function actually is in terms of things that you know, all right? In terms of things that you know, take a a problem that is not dependent on time, the Hamiltonian not being dependent on time. I use your normal Schrödinger description. The initial wave function, of course, can be written as a sum over eigenfunctions, right? Let's say, let me write it this way. Can be written like this, right? What happens to the later wave function? Well, all that happens is it accumulates a phase, right? If I can decompose the initial wave function in terms of eigenfunctions, then the later wave function just accumulates a phase for each term. But I also know what is an. By projection, I know an is given by the integral dx of the initial wave function, times psi n star of x. This is an. Right? If I assume the wave functions are normalized, then the coefficient an is obtained by projecting the initial wave function onto the corresponding eigenfunction. Now, I compare this expression with this expression that I have for the Green's function. You notice that the Green's function says that this thing is equal to dx times the initial wave function, right? Times something else. And all the rest must then be the Green's function. Therefore, I identify that the Green's function for x prime, x, and t is simply sum over n psi n star x prime, and it's conventional to write this in the middle. Okay? So if you know the eigenfunctions and the eigenenergy, then the Green's function can be represented by this infinite sum. Okay? Where x and x prime, one occurs in the wave function, one occurs in the conjugate wave function, and there is a phase dependent on which n you are talking about. Okay? So if you know quantum mechanics in the conventional Schrödinger representation, the Green's function, at least in some abstract sense, you know quite well. All right? That's just to explain what the Green's function, although I won't use this in the subsequent calculation. I just want to make sure that the Green's function does not seem too abstract to you by writing down a concrete representation. So I now tell you what the almost is. I now claim that the Green's function, as defined by this formula, is given by the path integral I just wrote down, where the sum over paths would be over all paths which start at x and ends up at x prime. Okay? So that is a precise description of the path integral formalism. So what I wrote down was not the wave function, but actually the propagator. Because all paths, you have to specify an initial point and a final point. And this describes the propagator from the initial point to the final point. Once you know the propagator, you have solved all the dynamics. Okay? Now, if you have a propagator and you sort of Fourier analyze it in the t variable, if you have this function, if you Fourier analyze it in the t variable, you would find it has terms of different frequencies. And if you can single out the term of a particular frequency, that tells you what the eigenfunctions are, if you want to go back to the time-independent problem. Right? If you want to solve a time-dependent problem, that is how things evolve in time, of course, that fundamental representation tells you everything. Now, of course, this cannot be a real derivation. In the sense, you can't really get quantum mechanics. You cannot really derive quantum mechanics out of classical mechanics, right? So this can only be a guess. And ultimately, you have to check that the guess agrees with experiments. And the way we check that it agrees with experiments eventually is to the simplest way, given the history of how all this developed, is to prove that it is equivalent to the Schrödinger equation, which, of course, has been checked against experiments in many ways, like the spectrum of hydrogen and so on and so on. Okay. Now, let me then come to the classical limit. This is actually very simple, just to relate how this, all this is connected to the classical limit. So let's say the red line is the classical path, and the dotted lines are all the other paths. In quantum mechanics, in a formal sense, the classical path has no special significance. I sum over all paths. Now, remember, a path is not an x of t that is classically allowed. It can be anything. It can be a crazy line that you draw. Right? I need to sum over all paths, and they all contribute equally, in the sense that they all have the same amplitude, just a different phase. But what is significant about a classical path? Suppose I take one path, the red path, which may or may not be the classically correct path even. Then I sum over all paths. I divide it into the following sense. I divide all paths into sort of bunches, right? This is one path. This is another path. That is another path, which are all quite different. And for each path, I sum over a number of neighboring ones. So this is a bunch, okay? So I divide all paths into a number of separate paths, each with a bundle around it, conceptually, okay? And that is sort of like when you do normal integrals by the trapezoidal rule, right? So you chop the whole range of integration into little pieces, where you take the central one plus the little bit around it. Same idea. So I take a path, not necessarily the classical path, and include some paths around it, around nearby paths, around the central path, which I call x0. And now let me look at the phase factor. S for any of these paths would be S0 plus delta S, where S0 is the phase for the central path, the red line, and delta S is the difference between the neighboring path and the central path within that bunch. Okay? Now, if the central path is not the classical path, then the moment you move a little bit away from the central path, delta S would be non-zero. Right? There is a first order change in the action. And of course, when you have a classical action, that change will be large compared to h bar. Okay? Say you have a ball traveling. Okay? Then if I consider neighboring path that differ by 1 part in a million, that delta S would be huge compared to h bar. So when you sum over all the neighboring paths, they all have phases which are very different by many units of 2 pi. And therefore, they will all cancel. Very little left. Do you understand? So although each path contributes about the same amount, let's say this is the classical path. This red line is not the classical path. This red line compared to that red line alone have the same amplitude. But if instead of calculating one path by itself, I compare one bundle to another bundle, the bundle around a non-classically allowed path will add up to nearly zero because they all have different phases. Okay? But if I take a path that is classical, I take the central path to be classical, then delta S, that is the difference in the path between the red line and the neighboring green lines, would be at least to first order 0. So all the terms would have the same phase, and there would be constructive interference. And the answer would be very large. Okay? So this is the idea of stationary phase. There will be no cancellation. So if this is the classically allowed path, this red line is another path. When you consider the corresponding bundles, this one will be huge. This one will be nearly 0. So in that sense, now formally I say in the limit h bar going to 0, physically, as I said last time, I mean in the case where all the actions are large compared to h bar, including all delta S. Then if I consider a bundle of paths, neighboring paths, only the bundle around the classical path will contribute. And therefore, that is the classical path. In that limit, that is the only path that is significant. That gives us a rather interesting perspective on Newton's law. Newton's law tells you why does it go on that path. The quantum understanding is that it goes along that path because all the neighboring paths are coherent, give you constructive interference. Whereas if it goes along another path, all the neighboring paths would be coherent, would not give constructive interference. Okay? So that gives you the classical limit, tells you why when h bar goes to 0, you need only look at the path with S being at least extremum. It turns out extremum is minimum. So in the limit h bar going to 0, only the paths around the classical paths are relevant. And that gives you the relationship, the conceptual relationship back from quantum mechanics to classical mechanics. Okay, any questions? I think we covered that lecture very quickly. Lecture is not computationally difficult at all, but mostly just conceptual linkages.
In the picture that you draw, that the paths always in the forward direction of time, but can the particle actually go to some strange path in the past and then go back to the time t2?
Yeah, good question. Yeah. Let's see. What do I mean? This is the sort of path I drew. Okay. Now, by path, I always means I also include an arrow. Okay. So the sequence of points is like this. So you ask, can I draw a path that goes like this? For example, if I ask that this is the initial point, this is the final point, right? Can I draw a path that goes like this? This is what you ask, right? With a segment that goes backwards in time. Right? Whether it goes up or down doesn't matter. Right? X increase, can it go backwards in time? Okay? This is a deep question that Feynman asked. And it turns out that in quantum field theory, you can. In quantum mechanics, you cannot. The reason is that this segment of path should really be interpreted as an antiparticle going this way, and the particle and antiparticle annihilated at that point. Okay, something like that. Okay, a path going backwards in time is like an antiparticle. It's interpreted. Now, how can you have antiparticles? That's only possible in quantum field theory, where the one difference between quantum field theory and quantum mechanics is that in quantum field theory, you allow particle numbers to change. You allow creation and annihilation of particles. You consider that possibility. Okay? If you consider that possibility, that is within the context of quantum field theory, then lines going backwards in time are allowed. And that has to be included. Now, whether or not I allow creation of particles is not just a mathematical point. It relates to the energy scale you are considering. Suppose I'm considering electrons. Then at energies much below mc squared for an electron, like about 1 MeV, I can ignore the creation of electron and positron pairs. Okay? Then you don't need to use quantum field theory. Then you don't need to consider this kind of path. But if I consider energies large compared to 1 MeV, certainly I will be creating and destroying electron-positron pairs all the time. Also in virtual processes. That is, it happens so quickly that before you know it, it recombines and so on. Then you have to use quantum field theory. You have to include this kind of path. And actually, by drawing these paths is sort of the next step to the Feynman diagrams. Okay? You just draw the Feynman diagrams. Now, that we don't have time to go into. It's mathematically more complicated. But I think conceptually, that's the answer. We will be staying with quantum mechanics. That is not quantum field theory, not creation and annihilation of electrons and positrons and so on. So in that context, I will not draw this kind of path. Paths only go forward in time. Okay? Now, once I do this interpretation, everything is still going forward in time, in some sense. Okay? I still regard this as going forward in time. All right. Any questions? Now, if not, I will go on to the next lecture. Okay? If we have time, next time we can jump ahead of Professor Yang and start talking about some symmetries. Because I think some of the later ones would take up a little bit more time. Oh, by the way, in all these lectures, in every topic, I will just tell you sort of the simplest ideas, the simplest examples. And I will encourage those of you that are interested to go to the references. And with the concept, I think you can start to learn more. Okay. So lecture 5, I will try to start from the path integral that I just derived. Not derived, actually presented. And from that, derive the Schrödinger equation. And that will show that what we have is equivalent to all the quantum mechanics that you have learned. Now, in the conventional presentation, you go to Feynman, Hipps, and so on, probably the derivation is the reverse. You start with a Schrödinger equation, you derive the path integral. That's okay too. Okay? And I will do it in a very simple way. And I will do this in 2 steps. One is just to go through some mathematical preliminaries. In fact, these have been assigned to you as homework. So I will be rather quick about this and just point out the key features so that we have some formulas that we can use. And then secondly, I will use those formulas to derive the Schrödinger equation. Okay? Now, just to remind you what we are doing, schematically, the wave function at time t is the Green's function times the wave function at time 0. Now, that is a schematic representation which is motivated by the discrete version. If you think of x as a discrete variable, say assuming values x1, x2, x3, then you can think of psi as a vector, say psi of x1, psi of x2, psi of x3, as a column vector, okay? So you can think of the wave function as a column vector. Then the Green's function is a matrix. So the formula that I wrote down before can be thought of as a matrix equation. The new column vector is the matrix G times the original column vector. All right, so just save some writing of integrals. All right? And the Green's function, I said, was is represented by this path integral. And I want to prove that this leads to this equation. Okay? Which, of course, you know about. Okay, so start with some mathematical formulas. Much of path integrals really has to do with Gaussian integrals. Okay, so let's start with the simplest Gaussian integral of e to the minus x squared. And that's just a constant. And that constant is square root pi. And you have derived it, all right? It doesn't really matter. If you don't know it's square root pi, just write it as some constant. That's good enough for the rest of the discussion anyway. I don't really care. But it's easy enough to derive as square root pi. All right? Now, if I put a parameter epsilon here, and I call this integral I0 of epsilon, and eventually I want to look at this kind of integrals when epsilon goes to 0. Now, intuitively, what does this mean? This means that the exponent is rapidly varying. If epsilon is very small, then you change x by a tiny bit, the exponent is already changing very rapidly. Okay? So think of very narrow Gaussians. We will be looking at the epsilon going to 0 limit. Now, although for this formula, it's exact for any epsilon, but later we'll take the limit epsilon go to 0. We are looking at very sharp Gaussians, where the integrand, the function in the integral, varies very rapidly. What happens? Well, in this case, that's trivial, because you just scale it by x prime is equal to x over square root epsilon. You get back an integral like this, right? So you find that this is the original square root of pi times epsilon to 1 half. Now, you can understand this very easily by just sort of drawing a picture. These are dependence, because if you look at that Gaussian, what is the typical width of that Gaussian? It is obviously square root epsilon, right? Order square root epsilon, because if x changes by about square root epsilon, then it peaks at x equal to 0. When x is equal to square root of epsilon, the exponent has dropped by a factor of e, right? So the width of that Gaussian is square root epsilon. So this curve has a height of 1 and a width of square root epsilon. So the area under the graph would be of order square root epsilon, right? I mean, just to understand the dependence without even having to go through this kind of mathematical change of variable. Okay. Now, let me call, instead of writing epsilon downstairs, I write epsilon as 1 over alpha. So I have e to the minus alpha x squared. So that's simple. That gives alpha to the minus a half power. So alpha is just 1 over epsilon. And the reason I do this is to help me get the next formula. If I differentiate the first line with respect to alpha, on the left-hand side, differentiate with respect to alpha, and then put a minus sign throughout. Then on the left-hand side, I differentiate under the integral sign. I just bring down a factor x squared, right? And on the right-hand side, I have alpha to the minus a half power. I differentiate, I get a half times alpha to the minus 3 halves power. And now I return alpha to 1 over epsilon. Okay? And I call this integral I2 of epsilon. The 2 meaning I have 2 powers of x in front. It's the second moment of this, then I get this function. Okay? And again, the power of epsilon you can understand very easily, because in this integral, I have 2 more powers of x, and the typical magnitude of x is square root epsilon, right? So 2 more powers of x gives me 1 extra power of epsilon. Right? The numerical factors, of course, you have to work out in detail. And you can easily see if epsilon goes to 0, the more powers of x you have here, the more powers of epsilon 1/2 you have in the result. Right? So this is very easy. Now I will use this. Now everything up to now is exact, even for large epsilon. But now let me look at the following, which is the sort of thing that occurs very often in many problems in physics. Suppose I have an integral that looks like this. I have a function f of y, which is arbitrary, multiplied by a Gaussian, which is e to the minus x minus y squared divided by epsilon, and integrated over y. The result, of course, depends on x. Okay? I want to evaluate this integral in the limit epsilon going to 0. Now, if epsilon does not go to 0, there's nothing much I can say about this integral, because f is unknown. F is just an arbitrary function. But you see, the idea is the following, before I go into details. If epsilon goes to 0, the Gaussian becomes very narrow. The red curve, the Gaussian becomes very narrow. The integral matters only when y is approximately equal to x, right? Because if y is very different from x, it is multiplied by a Gaussian, which is nearly 0. Doesn't matter. So the integral only samples those values of y near x. Therefore, it should depend only on f of x, f prime of x, f double prime of x, and so on. That is, it only knows this part of the blue curve, right? This part of the blue curve, if I only look at a very small part of amount square root of epsilon, can be represented by the first few terms of the Taylor series accurately. So you don't need to know all of the function f. You only need to know its first few derivatives around the point x. Okay? That's the whole idea of this kind of integrals. So mathematically, what I do is I write f of y. Now think of x as fixed. Okay? X is something fixed. Y is a variable that varies. I now expand f of y in terms of this Taylor expansion around x, as in powers of y minus x, which I will now denote by u. And the idea is that u can be regarded as small. Now, this is slightly tricky because if you look at the integral, u actually ranges from minus infinity to infinity. Right? If y goes from minus infinity to infinity, u goes from minus infinity to plus infinity. So u is not small in that sense. But nevertheless, I regard it as small and expand, because the large values of u will be multiplied by a very small Gaussian. Okay? So I do the expansion. So I just write this down. The Gaussian is now u squared over epsilon. I now do the expansion, f of x, u f prime of x, u squared f double prime of x, and so on. Now, in these integrals, f of x, f prime of x, f double prime of x are all constants as far as the integral over u is concerned. So I just pull them out. Then the first term is just the integral over a Gaussian, which is I0. The second term is odd in u, multiplied by this even function, integrates to 0. The third term, with a u square, then integrates to I2. All right? And now, using my previous result on what I0 and I2 are, I have an overall factor of pi epsilon square root, f of x plus 1/4 f double prime of x epsilon, and so on. So the square bracket, as you can easily see, will be a power series in powers of epsilon, of which I have shown just the first 2 powers. Is that okay? This technique is called the saddle point approximation, used in many, many problems in physics, right? Because the Gaussian looks like a saddle, right? And it is valid whenever the saddle becomes increasingly narrow, increasingly sharply peaked. Is that all right? So you have done this, but I just want to go through this very quickly. Now, the version we want to use is actually slightly different. We have actually an I here. Okay? It's not minus something over epsilon, but I times something over epsilon. Now, the idea is still the same, although the argument is slightly different. If you have a minus sign in the Gaussian, in the exponential, you focus on the points y nearly equal to x, because away from that, the amplitude dies down very quickly. If you don't have a minus sign but an I, then what do you have? You have, let me use the representation e to the iu squared over epsilon. If u is 0, and I change u by a tiny amount, the phase is unchanged to first order, right? Change only by u squared. Okay? But at any other point, suppose I write it this way, u is equal to u0 plus delta u. Then I write this down, this is e to the I u0 squared over epsilon, e to the 2I u0 delta u over epsilon. If you look at the second factor, if u0 is not 0, then any change in delta u will change a significant, change the phase significantly, right? Say if u0 is equal to 0.1 and epsilon is very, very small, then even if you change delta u by a tiny amount, the phase will be changing a lot. So the sum over delta u, because when you're integrating over u, you're just summing over different delta u, right? Around that u0, which is non-zero, will take in terms that have very different phases, and therefore they will cancel. All right? So this is the same argument as the argument of the cancellation of phases over paths. Right? Exactly the same. All right? But here is actually a simpler context. It's not a path integral. It's just an ordinary integral. Okay? So again, it will be dominated by the point where the exponent is minimum, okay, or is stationary. Okay? So it is like the saddle point approximation, but not with reference to the magnitude, but with reference to the phase. Now, in a mathematical sense, you can sort of forget about all this and simply do a substitution, because from the previous problem to this problem, it's just changing minus 1 over epsilon to I over epsilon, or in other words, changing epsilon to I epsilon. So you just take the previous formula and change epsilon to I epsilon, you get this formula. Right? So you can think of it as analytic continuation in epsilon, if you like. All right? So you get this formula. And this goes under a slightly different name. It's called the approximation of stationary phase. When you are summing over many things where the phase could be changing rapidly because epsilon is going to 0, then the dominant contribution comes from the point where the phase is not changing. Right? In this representation, if u0 is equal to 0, then to first order in delta u, the phase is not changing. Right? So again, you get, in the square bracket, a power series in epsilon. Any questions? This you have done. I just repeat this. All right? So I think we have time today to complete this lecture. I think we still have nearly 45 minutes. You will use this to now derive the Schrödinger equation. Now, the formulas in the middle will look slightly complicated, slightly messy. So you don't worry about all the factors, but focus on the main factors that we will be working with. You can go back and check everything else. All right. Now, this is, sorry, I have, the first formula is actually wrong, but it's okay. Let's consider the path integral. That takes you, because this is the right-hand side is the path integral, it's just a propagator. It's not the wave function. You have to multiply by the initial wave function and integrate. I missed one factor. But doesn't matter. You have some initial wave function, say at t equals 0. I now want to calculate the wave function at t plus delta t. Okay? So what do? I chop up the time interval into many pieces. So here, I chop up the time interval up to t, and then one more interval. Okay? So I want to propagate the wave function from time equal to 0 to t plus delta t. So I chop the t up to t, and then one more step, t plus delta t. Then the path integral tells me that I have to integrate over this x, this x, this x, this x, this x, and then this x. All right? Let's say I chop it up into 1,000 plus 1 intervals. Then I have to, this path integral involves 1,001 integrals. All right? Now, if I first carry out the first 1,000 integral, that will propagate the wave function up to this point. I don't know what it is, but that answer would be the wave function at the time t. All right? If I just do the first 1,000 integrals, I will get the wave function at time t. And let me call the value of x at this point x double prime. Now I carry out the final integral. The final integral means x double prime is arbitrary. I now integrate it as e to the I delta s over h bar. Delta s is the action from here to here. Okay? Now, here I am using the fact that the action is additive. Because I start off with e to the I s, where s is for the whole path, but I can write the total s as the sum of the delta s for each segment, and I isolate the last segment and put it here. For all the previous segments is contained in the first messy integral. Do you understand? So to go from 0 to t plus delta t, I chop it up into, let's say, 1,001 intervals and do 1,001 integrals. The first 1,000 integral gives me the wave function up to time t. Then the final integral will take me from t to t plus delta t. So I get this, I reduce the path integral formalism to this expression, which tells me by using one integral, now this is not a path integral, this is an ordinary integral, okay? Because I'm integrating over one value of x, namely x double prime. By integrating, doing one single integral, I relate the wave function at time t to the wave function at t plus delta t. So that is the first conceptual step. Do you understand? So this is the path integral using just one short interval. So that is the expression I want to use. Because think about it. What is Schrödinger's equation? Schrödinger equation tells you what d psi over dt, what's the time derivative of psi. The time derivative of psi, in fact, tells you how is psi at t plus delta t related to psi of t, right? So once I evaluate this expression, I will know how psi of t plus delta t is related to psi of t. And that should check with Schrödinger's equation. All right? So that is the idea. Now, of course, I'm not a mathematician and so on. Everywhere, of course, we have to imply delta t going to 0. Okay? To simplify writing, I will change x prime to x and x double prime to y, just to write a few so that I don't have to bother with primes. So this is the expression I will start with. That wave function at x at time t plus delta t is related to wave function at y at the earlier time by a phase factor e to the I delta s over h bar. Delta s is the action for that small section of path. So this path at time t was at y. You see, at time t the particle was at y. At time t plus delta t it is at x. So it is the action for this path. Because it's a short segment of path, I assume it is a straight line. All right? So it is now an ordinary integral. So let's write this down. What is delta S? Well, delta S, S is the integral of the Lagrangian. For such a short interval, the integral of the Lagrangian is just the Lagrangian times delta t, right? It's the integral over a short interval. You don't have to do the integrals, just multiply by delta t. So the square bracket is the Lagrangian. The Lagrangian, the first term, is the kinetic energy, m over 2 times the velocity squared. What is the velocity? Well, the particle went from y to x in the time delta t. So the velocity is x minus y divided by delta t squared. The potential energy is the potential energy, say, at x. Now, of course, the particle is moving from y to x. But y and x are very close because I'm talking about very short time interval. So I can regard the potential energy as constant and simply call it V at x. Now, you can always look at the next term and you can verify that the next term vanishes when I take delta t goes to 0. Okay? And so delta S is given by that first line. Is that okay? So I stick this into the exponential. The exponential is e to the I delta S over h bar. So first of all, the kinetic energy term divided by h bar, and then the potential energy term divided by h bar. Is that okay? Eventually, delta t will be going to 0. So just so that we can make use of our previous expressions, let me call all this bunch epsilon. And epsilon is 2h bar delta t over m. And eventually, this is going to 0. Right? Now, it's going to 0 not because h bar is 0. Not because h bar is being taken to 0, but because delta t is being taken to 0. I make no assumption that h bar is small. In other words, I make no assumption that the actions are large in units of h bar. Because if I talk about hydrogen atom, rather than a ball, rather than a billiard ball, the action is not large compared to h bar. Okay? So here, epsilon going to 0 does not rely on h bar being small, but relies on delta t going to 0. Okay? And in this term, I expand this exponential in powers of delta t. So I get 1 minus this thing, delta t. Now, it's clear that all this calculation I only have to carry out to first power in delta t, because I'm looking at the wave function at t plus delta t. It will, of course, be equal to the initial wave function plus a term proportional to delta t, right? The term proportional to delta t will then give me the time derivative, the first time derivative, which is the only thing I care about. If I can find the first time derivative, that will give me the Schrödinger equation. Right? I don't care about the second time derivative, so I don't care about delta t squared. That is why the potential energy term I evaluate to first order. All right? So this is what we have. So I just put it into the formula. You see that the later wave function is given by the initial wave function multiplied by the action and then integrated over y. And I have pulled out, let me go back. Look at this square bracket. So this is an exponential involving x minus y. This square bracket involves only x, does not involve y. Okay? So anything that does not involve y can be pulled out of the integral because I'm integrating over y and x is being regarded as fixed. All right? Is that okay? Think of the square bracket as e to the I with a v. Okay? It's an exponential e to the iv something, which I have expanded and brought down. It just means, you see, as the particle moves from y to x, for the potential energy term, I can regard the position as constant. For the kinetic energy term, of course, I cannot. Because although y minus x is small, in the kinetic energy term, I'm dividing by delta t, which is also small. All right? So I have this expression. Now, this is, of course, this integral. Now, I just keep this square bracket unchanged. this integral is exactly like the saddle point integral we just discussed, right? It is a function of y multiplied by an exponential e to the ix minus y, where there is an epsilon which is going to 0. Remember our previous discussion that this is equal to square root of pi I epsilon. The n I just copied, all right? That's just normalization. Times the value at x, and then a term, the second derivative at x, multiplied by 1 power of epsilon. Okay? So just so that you can see everything together, let me write a saddle point formula on the board, and that is e to the I x minus y squared over epsilon, the function of y dy is equal to square root of I pi epsilon, function at x plus, I think, maybe 1/2 or something. 1/4, 1/2, 1/4, I don't know. Some numerical factor f double prime of x times I epsilon. Right? So that is the saddle point formula that we derived earlier. That such an integral, when epsilon goes to 0, although you are integrating over all y, it is sensitive only to the value at x and the derivatives around x. And the higher derivatives are associated with higher powers of epsilon. There is a numerical factor here you can work out yourself. Right? So that is what we have in the second line. Is that okay? Now, look at the part in blue. I haven't told you what the normalization constant is. But it must be chosen in such a way that it gives the correct answer when delta t is exactly equal to 0. So if I look at delta t exactly equal to 0, what would happen? Forget about the blue part. If delta t goes to 0, this term goes away. This term goes away. So the black part would simply give you psi of x and t. Right? The first bracket is 1. The second bracket is just psi of x and t. This one goes away. So the normalization factor, when delta t goes to 0, this is also psi of x and t. So for the normalization to be correct, this n must cancel the square root. In fact, that n has to be equal to 1 over this thing. Okay? That is how the normalization constant is chosen. So the blue part can simply be dropped. Okay? All right, now we expand. We multiply out the two black brackets and organize terms according to powers of delta t. The 0 order would be the 1 times the psi. So it's here. The first order, there are two terms, one coming from here, which is this term, and one coming from here, which is this term. Okay? Any questions? Now, the cross term, this times this, the second term in this bracket multiplied by the second term in this bracket would be delta t squared, which I don't care about. To first order in delta t, there is this term involving the potential energy, and that term involving the second spatial derivative. Okay, so the second spatial derivative. Is this okay up to this line? Now, you will have to work out the factors, how many h bars, how many m, and so on. I mean, that is detail, what you need to look at. Now, just so that you step back one step and just recall, the V comes from the potential term in the action. The second spatial derivative term comes from here. Okay? And the reason it comes from here has to do with this power, and this y minus x over delta t squared is the kinetic term. Right? The kinetic energy is the displacement divided by delta t. That term in the action causes the second derivative term here. And that is the reason for this term. Is that okay? Now, if I move this term to the left-hand side, what would you have? The left-hand side would be the difference in the wave function between t plus delta t and t. So that is, of course, just the partial derivative with t times delta t, if I move it to the left-hand side. Okay? Move this term to the left-hand side and combine with that term. These two other terms all have a power of delta t, which I pull out. Okay? So I have one term which is second spatial derivative and one term which is v. So I just copy that line. The first line is copied. Then I just cancel a delta t and multiply throughout by IH bar just to render it into a conventional form. And this is, of course, the Schrödinger equation. All right? That the time derivative of the wave function is just the kinetic energy operator, right? The potential energy times psi. Now, I don't think I need to go through detail and check all the H bar factors and minus signs work out. I mean, that's details that you could check yourself. Right, so that finishes the task of deriving the Schrödinger equation starting from the path integral. So now, although the intermediate calculation is, needs a little bit of care, but I think the idea is very simple. Let me summarize. Classical action S, e to the is over h bar for one path, sum over all possible paths, that leads to a path integral. But if I propagate not from 0 to t plus delta t, but only from t to t plus delta t, then it does not involve many, many integrals, but just one. And by carrying out that one integral in the saddle point approximation or the stationary phase approximation, which is justified because delta t is going to 0, I recover the Schrödinger equation. And that proves that the formulation of quantum mechanics which Feynman proposed is correct, because this is correct. This is checked against experiment in a million different ways. Right? So that is a particularly neat, okay, so that's a summary. Okay? So starting from Newton's laws, we show that this is equivalent to the least action principle, delta S equal to 0. You raise it to the exponential as the phase, EIS over h bar. And the path integral is a statement that the Green's function is given by such a path integral, which means many, many, many integrals together, say 1001. And if I just look at the last one, then I get the Schrödinger equation in this operator form. Now, although I did it only in one dimension, it's obvious how you generalize through 3 dimensions. Okay, so that's the end of the story, and I hope you will remember this picture, this logical relationship, which is a very elegant way of going from F equals to ma to the Schrödinger equation. Using ideas that you are really familiar with, the path integral really comes from ideas of phase, interference, multiple slits, those ideas being drawn together, and many, many multiple slits, and that is how you arrive at this picture. Right? And I think you have enough of a framework such that if you like, you can go read the first few chapters of Feynman and Hibbs on your own. By the way, I have quite a bit of time left. I could say 2 more things. One is this is what's called the Lagrangian path integral, because it involves the action, and you integrate over x. There is another version which is actually used somewhat less these days, called the Hamiltonian path integral, which involves something like this: dx dp e to the minus ih of x and p. I think this is probably dt. I think something like this. You see, suppose I chop the time interval into 1,000 intervals. The Lagrangian integral I wrote involves 1,000 integrals, right? The Hamiltonian integral involves 2,000 integrals. That means for each time, I choose one x and one p. So at each time, I do not describe it by just a position, but by x and p. So in other words, at each time there is a phase space. And the path is described by how the particle moves through phase space. And it does not have to move satisfying Newton's laws. That is, nobody says that P has to be equal to mx dot. Does not need to satisfy this. All right? That is a classical equation. But when I sum over quantum mechanical parts, I don't need to obey that equation. So I have a 2,000-fold integral. And you can show that this gives the same answer. Okay? And the reason for this is actually not that difficult. No, is this? Oh, there is one more factor here. dt, and then I have to, I think, take away x dot p. dt, or is a p dx? It's the same. The reason is actually very simple. In this expression, p occurs quadratically because it occurs as p squared over 2m in the Hamiltonian factor and as linearly p in the second factor. Whereas x can appear in very complex ways, all right? Because the potential can be a complicated function of x. But p in this expression occurs quadratically. An integral with e to a quadratic, you can always calculate exactly and get rid of it. So that's how you show that this one is equivalent to this one. You can do all the p integrals exactly without approximation because it's quadratic. And by the way, that also shows you that the harmonic oscillator can be solved exactly. Because for the harmonic oscillator, the action is quadratic in x. And e to a quadratic, you can calculate exactly. And so that is why, from this point of view, the harmonic oscillator is exact. Okay? Any questions? Now, so that is one comment. The second comment, just a word, schematic again, because I haven't prepared. I am not sure I will get my factors right. Perhaps I should put on the light a bit. Tell you about analogous ideas in statistical mechanics, quantum statistical mechanics. Now, you have all studied. They are doing it. You have learned. Now, how about this formula? Do you know this formula? That the partition function is the trace of e to the minus beta h.
Do you know that?
Okay, you all know. All right. So what is this? What is the trace? Trace means you sum over, you take the diagonal matrix element and you sum over the diagonal, right? Yeah, and you sum over all possible values. So if I take the trace in, say, position representation, that is the answer. Okay? Now, I will always think of sum and integrals as interchangeable. Okay? Now, I do the following. I write this as let me call this x0. And delta beta is beta over n. Right? I chop beta into n intervals. Think of there is a beta axis, okay? Think of a beta axis. So this is 0 to beta, and I chop it up into little pieces, delta beta. So that is okay, right? That's just writing an exponential as a product of many little exponentials. Oh, by the way, you can't do this. Oh, did I do this right?
You want to go imaginary time?
No, I don't want to go imaginary time. There are some slight tricks about whether or not you can do this. That is, whether or not e to the a plus b is equal to e to the a times e to the b. It's not always the case, but here they all commute. So in time-independent Hamiltonians, they all commute, so that's okay. Now, but I can also do the following, right? I can insert a complete set of states in the middle. all possible x1s. That the red part is the identity, right? That's something you learn in quantum mechanics. Okay? So if I do this everywhere, what do I have? Sum over x0, sum over x1, sum over x2, blah, blah, blah. So I have essentially a path integral, right? Because I sum over x0. So think of this as like a time axis. So here are the possible values of x0. Here are the possible values of x1, x2. So I have a path integral over x. That means sum over x0, sum over x2, sum over x3, and so on, right? And what do you have? This is then an element like this. So this is like the product of xn e to the minus delta beta h xn plus 1. Okay? And if you work this out, this is a path integral very much like the one we have described. And in fact, as Professor Hui says, if I regard this as it over h bar, it is like a path integral in imaginary time. Okay? And this thing, if you work it out, is actually very much like the action that we have written down. I won't go into detail here. Right? So quantum statistical mechanics can also be written rather like a path integral with several features. One, it is in imaginary time. Two, beta is somehow related to t. It's the analog of t except for the factor of I. Third property is very important. The initial x and the final x are the same because I am taking a trace. So it is a path integral over all cyclic paths. The path must return to the same point. Okay? And at least many of the techniques that are developed for calculating quantum path integrals can be applied to quantum statistical mechanics. Now, it's not seldom used in elementary courses, but in advanced courses where you want to do perturbative calculations, whatever, sometimes to relate quantum mechanics to statistical mechanics by a complex rotation in time, changing t to it or something, all right? That is actually a very interesting, at least mathematical connection. The techniques are very much the same. And you see how the idea of a path comes in because you choose a value of x at each slice. Here, slice is a slice in beta. Okay? Oh, by the way, why do you have to chop it all up? I have to explain. The reason you have to chop it all up because eventually, when you do this, how you evaluate this will have a kinetic term plus a potential term. So essentially, what you want to do is, anyway, never mind that. You split the kinetic and potential terms. That is possible. Now, these two terms do not commute. So this is not satisfied. All right? But that is possible because if delta beta is small, the error when you do that is delta beta squared. And eventually, when you do the path integral, of course, you imagine delta beta going to 0. Okay? And that is the sort of one reason, technical reason, why you need to chop it up and insert everything in the middle. And therefore, you can have the kinetic term and the potential term, which you can then evaluate. Once you evaluate, they are not matrix elements, but explicit exponentials. And it looks very much like what we have written down. I won't go into detail, just to give you a hint in case you want to read up about it. Okay, so that's really all I have today. Any questions? We are one lecture ahead of time.
Now the system is relativistic, yeah. And is it possible to find a description of the quantum mechanics by path integral?
Yes, absolutely.
Just replace the action by relativistic action?
Yes. But you probably then would not recast it into the Schrödinger form? Now, okay, that's a very good question. Let's see what happens for relativistic cases. For relativistic cases, let me calculate the propagator from the point, say, x, y, z, t, to the point x prime, y prime, z prime, t prime. Okay? Now, I do not even draw the axis. So it's just from one space-time point to another space-time point, like this. Okay? What is this propagator? This propagator is then the sum over all paths. Now, schematically, like this, e to the I s over h bar. Now, what is a path? It's just all possible lines like this, which are time-like. I'm not even sure you need to impose the requirement that it's time-like. I'm not sure about this point. But I mean, as far as the abstract description is concerned, I don't have to tell you about the coordinate system, right? I draw a path in space-time. Associated with that path is an action. Okay? Now, what is the action along a path? I can certainly write it as the following, that delta S, well, let's see, delta S is just delta x mu, square root minus m. Right? That is an invariant expression for a free particle, right? So at least the starting point is completely invariant. So I guarantee the quantum mechanics will be invariant. Now, you would not, now in this derivation that I just carried out, I chose time as the independent variable. I asked what happens if I go from t to t plus delta t. Once you choose t as an independent variable, that means you have chosen a particular set of axes in Minkowski space, this t, and not in an accelerated frame, which would be sort of that t, right? Okay? And once you have chosen to represent things in a particular reference frame, you would have broken explicit Lorentz invariance. It will still be correct, but not explicitly covariant, and in many cases, perhaps not the best way to represent the physics. And that is actually one reason why, once you go to relativistic cases, the action formalism is a much better starting point than the Hamiltonian formalism. Because you from day one, line one, that everything is covariant. Okay. Any other questions?
Professor Yang, I would like to ask a question. Just before you just take h bar to 0 to get the classical limits of the quantum mechanics. So why can we just simply take h bar to 0 in the Schrödinger equation to get the classical limits?
Oh, you can.
You can?
Yes. Now, but of course you can. But it's very tricky in the Schrödinger equation. It's a singular limit. See, if you take h bar going to 0, I mean, that goes to 0, that goes to 0 even faster, and you get only this term. That is sort of correct, that v of x, take the time-independent equation. Right? Now forget about the left-hand side. Then it says v of x psi is equal to E psi. What does that say? It says the particle sits at the bottom of the potential with the energy equal to the value of the potential energy. That's correct in a classical sense. Okay? But if you look at the wave function, it's rather, look at everything, it's rather tricky. It's a singular limit. And the proper way of taking that limit is actually the WKB approximation. Have you learned the WKB approximation? You see, well, that's not all that difficult. Let me see what, you haven't learned the WKB approximation? Huh? How's that possible? Huh? Let me just do a non-relativistic case, all right? So you have something like this, minus h bar squared over 2m derivative plus this equal to psi equal to E psi. All right? Let me write psi as e to the I phi. Then the second derivative, let me do a one derivative, would be I phi prime e to the I phi. If I do two derivatives, I would get, now one term with, I differentiate this again, so I get I phi prime squared. The other is I phi double prime. Okay? Is that all right? Now, let me see if I can explain what is roughly happening. Let me draw a picture. Suppose the potential goes like this. And the wave function, what does the wave function look like? Well, the wave function looks like this. Okay, so this is psi. Right? Now, there are two length scales. One is the wavelength of the wave function. One is the characteristic length over which the potential varies, which let me call L. Right? Now, in many problems, lambda is much smaller than L. And that is really the h bar going to zero limit. Because what is lambda? They broadly tells us that lambda is h over p. All right? V is a classical variable. Suppose you are talking about a classical problem, a ball tied to a spring. Then V of x is a classical function. It varies over distances of meters or centimeters. So L is a macroscopic length. Okay? P is a macroscopic variable. If you have a ball tied to a spring, it is, order 1 times kilogram meter per second. That means lambda is very small, right? Lambda is h over p, is very small. So you have lambda much, much smaller than p, than L, all right? Now, when I say lambda much, much smaller than L, that is like the classical limit because lambda is proportional to h bar. Now, let's see what happens then. If the wave function goes like this, phi prime, the wave function is, what the wave function should look like. The phi, goes like this. Goes like k times x, right? The wave function goes like wave number times x. Except the wave number is changing. Because think about, let me just write this. Right? They broadly tells you something like this. P, think of P as the classical momentum. So as the particle moves along V, the classical momentum is changing. Right? So phi prime goes like this. Okay? So phi goes like this. So phi prime, phi actually does not go like this. I have to write it more carefully. If I look at a small interval, the increase in phi is this amount. So phi prime is k. Okay? And phi double prime is what? Well, phi has a typical value k, and k is changing over a characteristic length scale L. So phi double prime is order k over L. Is that okay? Because it is k changing by maybe a factor of, maybe changing by 50% over a length L. That's the order magnitude. So if you look at these two terms, phi prime is order k, so phi prime squared is order k squared. Phi double prime is order k over L. So the ratio of the two terms, the second term over the first term, is k over L divided by k squared, is 1 over kl. And up to factors of 2 pi, k is 1 over lambda, right? So the ratio of the two terms is the ratio of the two length scales. One is the quantum mechanical wavelength. The other is the macroscopic scale. And this, of course, involves h bar, right? So this goes to 0 in the h bar going to 0 limit. Okay, so the h bar going to 0 means I can neglect this term. Now, this is the essence of the WKB method. You look at the phase, the first derivative of the phase squared is more important than the second derivative of the phase. The ratio involves h bar, involves a quantum mechanical scale to a macroscopic scale. Now, once I do this, of course, this equation becomes very simple. This equation, the I squared gives me a minus sign, gives me h bar. This derivative becomes d dx, right? D phi dx squared. Okay? And the solution to this is, of course, very easy. D phi dx is then equal to 2m over h bar squared e minus v of x. Everything square root. Right? So phi is equal to then, well, let me write the wave function. The wave function psi is then exponential of what? I times 2m over h bar squared dx. Right? Because it's the first, after I take the square root, it's just the first derivative, and I can just integrate. But if you look at this, this is sort of what we started intuitively. It says that the wave function increases, the phase increases in a way. And if you look at this, this is, you see, just if you forget about, take the h bar square out. All this is just the classical momentum p of x. Right? If you have a particle of energy E moving in a potential V, just classical mechanics, p squared over 2m plus v equals E, just give you, this is the classical momentum at that point. The momentum divided by h bar is k, the local k, and you just integrate this. All right? That's the WKB approximation. And that is how you obtain an answer to order h bar, to leading order in h bar. Now, this is trivial. You want to do it slightly more carefully to get the next term. Okay? And the next term involves, I think, something like E minus v to the 1/4 power, I think. Something like this. So that the wave function does not have the same amplitude everywhere. Okay? And the physical reason for that is also easy to understand. That actually has a classical picture. Is it 1/4 power or 1/2 power? I can't be sure. The idea is very simple. Think of a harmonic oscillator or a potential like this. So the particle is going like this, right? In the classical picture. It's going much more rapidly here. Okay? So if I look at a certain delta x, the probability of finding it at the bottom is larger or smaller. Now, since I got it backwards. Have I got it backwards? But that cannot be right for the ground state wave function. I mean, think of a harmonic oscillator, you should have a higher probability of finding it in the middle, right? I got it upside down. I think I got it upside down. Upside down? Carry this out to one more order. It goes, I think it's, maybe it's a positive. Yeah, I think it's correct. Is this correct? If V is the smallest, no, something is wrong. So forget about this formula. The intuition is wrong. Classically, it goes like this. That means it goes faster here. That means have smaller chance of finding it here. But I know the ground state wave function is biggest here. So something is wrong. Yes, you can get an approximate ground state wave function for any E. Approximate wave function for any E using WKB. And in fact, in general, it's more accurate for large E. Right? Why? Because for large E, the classical action is many times h bar. And the approximation h bar is small, becomes more accurate. Now, it turns out for the harmonic oscillator, I think the WKB approximation happens to be exact. Now, that's an accident of life, but it's not general. The prefactor, you can work it out. I'm sure it works out. I cannot do it right off. Okay. So that, now, let me come back to here. See, h bar appears in a rather complicated way. If you look at this expression, the limit h bar going to 0 is a very singular limit, right? And the thing you are interested in, which is really psi square, very, very often, right? Absolute square, is really independent of that h bar to leading order. So you can't simply, take the limit too naively. It's a mathematical. It's part of what's called asymptotic, singular asymptotic limits. You have to. It's a bit tricky, right? Okay. So that's a long answer to your question. Okay. So that's it today.